All right, I appreciate you working with me and letting me do this outside of class so we could kind of get through a little more lecture. But I want to go back and revisit a few of these problems in Chapter 5. This one's Your Turn 519, and it's got three parts. A says, based upon this formula for coal, how much carbon would you burn if you burned 1.5 times 10 to the 6th, or 1 million tons of carbon? How many tons, million tons of coal, how many tons of carbon would you burn? And so actually, if we know the breakdown of coal is this formula: 135 carbons, 96 hydrogens, 9 oxygens, 1 nitrogen, 1 sulfur, and that's very approximate, right? We could come up with a molar mass, it's pretty high, of 1,908.2 grams per mole. And then relatively speaking, we know the amount of carbon in 1 mole. So we have this ratio. We have the 135 carbons, or 135 times 12.01 grams of carbon in 1,908.2 grams of coal. I hope that makes sense. And actually, one more thing, if that's the relative grams of carbon to grams of coal, we could scale that up. Instead of grams, we could go tons of carbon to tons of coal. So let me know if you have any questions how that works. Because then, if we go that route, then our tons of coal will cancel, and we will be left with tons of carbon that would be put out if we burn that much coal. And so rounding to two significant figures, I get 1.3 times 10 to the 6th tons of carbon. The next question then is how much energy would be released if we, based upon 30 kilograms of 30 kilojoules of energy per gram of coal. And so here we go. Again, if we're going to go ahead and burn 1.5 times 10 to the 6th tons of coal, they gave us some useful conversions to get from tons to grams like this. So there are 1,000 pounds in 1 ton. Now remember, I'm doing this so tons will cancel, tons of coal. And then they also gave the relationship between pounds and grams. There are 464 grams in 1 pound, so the pounds will cancel, be left with grams. And now I'm ready to go ahead and insert that energy per gram that they gave me. They said for coal we can generally go with 30 kilojoules of energy per 1 gram of coal. Again, looking at things that cancel, everything cancels except the kilojoules of coal, which is exactly what, kilojoules of energy, which is exactly what I'm after burning that 1.5 times 10 to the 6 tons of coal. So burning that much coal, you're looking at 2 sig figs, that you're looking at 4.2 times 10 to the 13th kilojoules of energy will be released. And then the last one is what mass of CO2 will be released in this specific burning of 1.5 million, or 1.5 times 10 to the 6th tons of coal. And so let's see. So in order to work this as a side, I worked that the molar mass of carbon dioxide is 44.01 grams per mole. And you'll kind of see where that works into the problem. So if we start with 1.3 times 10 to the 6th tons of carbon will be released, and actually that's from A. And then I recognize in carbon dioxide, okay, if you have 44.01 grams or tons of carbon dioxide, that means you'll have 12.01 grams or tons of carbon. And actually got that from the molar mass. I hope that works for you. So if it works for you, then tons of carbon cancel, and actually it's totally legitimate. Tons of carbon cancel, we're left with tons of carbon dioxide. And rounding again to two significant figures, you're looking at, oops, looks like I have a typo here. I can add that. You're looking at 4.8 times 10 to the 6th tons of carbon dioxide. Okay? All right. The problem, my answers are slightly different than the textbook, but back of the book, but they're close enough. Okay, so the next one, I want to take a look at 523, and it was a related question. And let me pull it up here. Your turn. 523. Okay, so it says that now we're switching gears to natural gas. The formula for natural gas, it's methane, is CH4. That's the major component anyway. I would imagine it's a mixture, but I don't know. The amount of energy in the problem, it says, is there's 50.1 kilojoules of energy per gram of methane that's burned. And the first one is we're supposed to calculate the mass of CO2 that would be released if we're trying to crank out 1,500 kilojoules of heat. So those are the 2 molar masses that you're going to see me use down here. So I'm going to start with the amount of energy we're trying to crank out, 1,500 kilojoules of energy. And then I'm going to go ahead and use that 50.1 kilojoules of energy per gram of methane. All right. So I'm after gram of CO2, and I think I'm going to do it this way. Yep. I'm going to go in methane, in CH4, the molar mass is 16.04 grams per mole. So I can go in 16.04 grams of methane, I will have 12.01 grams of carbon. Again, this is a similar approach as I used on the last your turn problem. Well, at that point, kilojoules will cancel, grams of methane cancel, I have grams of carbon. I can go ahead then and relate grams of carbon to grams of carbon dioxide this way. The molar mass for carbon dioxide is 44.01 grams per mole. So then that means, relatively speaking, I have 12.01 grams of carbon and 44.01 grams of CO2. I notice I need my grams of carbon to cancel, so I'm going to do it this way. Okay, so actually, if I look back over my units are there. That will give me grams of CO2 released when I burn methane to release 1,500 kilojoules of energy. Rounded 2 significant figures. This surprised me. I don't know if it surprised you, but I came up with 82 grams of CO2 gas. I think that's interesting. A follow-up question then was to go ahead, and I had a little table 5.2, and you're supposed to pick a coal, and I picked the same one that your author picked. I picked bituminous coal from Maryland, and go ahead and do a similar problem with the goal of cranking out 1,500 kilojoules of energy. So in this case, we're going to go with the energy output for this particular grade of coal is that 30 kilojoules per gram that we've used before. We're going to go with, this is the formula for coal, and it has a molar mass of 1,908.2 grams per mole. So if our first term is that 1,500 kilojoules of energy I want to crank out, then I'm going to go ahead and insert my energy released per gram of coal burned. Okay, and then I need to go ahead, I'm on my way to get grams of CO2, and I think we used something kind of like this in the previous problem. For coal, since in the formula of coal I have 135 carbons in one repeating unit. If I put 135 times the decimal number for carbon, 12.01, and I divide that by the entire molar mass of a coal molecule, 1,908.20 grams, then that's the relative mass of carbon to mass of coal. Okay. So in this case, my energy units cancel, my grams of coal cancel, I'm left with grams of carbon. Now I need to get to grams of carbon dioxide, so one more term should do it. If I put 44.01 grams of CO2 over 12.01 grams of carbon, and that's legit, that's the real deal with carbon dioxide and carbon, then my units of grams of carbon cancel, I have grams of CO2, which is perfect. And I need to round according to sig figs. I'm going with 2 significant figures in my 30, which I'm not sure if I really should, but so I ended up with 160 grams of CO2. And then if we compare the mass of CO2 released by the methane, which is 82 grams of CO2, versus the mass of CO2 gas released by burning coal, you can see why they say methane, or we can see that methane is a cleaner gas in that sense. Okay, one last turn it in problem, or your turn problem. In this one, let me pull it up. It was a little bit different than the others. Oops. Okay, so we were supposed to draw the structural formula for cracking this 6-carbon alkane. And when and actually that was given in your textbook, equation 5.9a and b. And so thermal cracking leads to this, where you have your products are actually the C11H22, that is an alkene, and the C5H12, that's an alkane. So we're supposed to draw those structural formulas. So this actually, I'm kind of cheating a little bit. Every time you see a dash that has nothing at the end of it, for me, there's a hydrogen at the end of that. So I hope that's okay with you. You can see I've drawn the skeleton, the carbon skeleton structure. At the end, I drew a carbon double bond carbon. Okay, so that's my C11H22. Go ahead and count the little dashes if you want. I have, and I got 22 hydrogens connected to those 11 carbons. So my C5H12 is actually an no double bonds, so it looks like this. You can see the 5 carbons and the 12 hydrogens. All right, so that was A. And then B and C ask you to go ahead and see if you can see a pattern. And the pattern for number of hydrogens for an alkane, where there's only single bonds, is 2 times the number of carbons plus 2. Or 2n plus 2, where n is equal to the number of carbons. Then they said, go ahead and consider, well, what if you have just one double bond? Well, if you have only one double bond, then actually the way that works out is the number of hydrogens is going to be equal to 2 times the number of carbons, or 2n. Yep. Okay. So the last one, oh yeah, okay. The last one I thought was kind of interesting. They gave us these 3 hydrocarbons, and we're supposed to kind of do what we did before with boiling point temperatures. Remember, the larger the molecule, in this case with 16 carbons, they'll have more electrons. So even though it's a what we say nonpolar molecule, you have more electrons that can kind of slosh around, and you can get those partially negative. You can get those electrons to give a partially negative region, and that actually makes those London force connections, so it's intermolecular bonds. So anyway, so more electrons, most London forces. Over here with 5 carbons, least number of electrons, least degree or strength of London forces. So you would expect then the one with 16 carbons to have the highest boiling point temperature, because what's happening when we boil, when a liquid goes from when a substance goes from a liquid to a gas, is we're breaking some of those London forces. So the more they have, the higher we have to jack up the temperature. Compared to the lower amount of London forces, the lowest boiling point temperature. And then actually it said go ahead and look them up on the internet, and I did. So yes, the hydrocarbon with 16 carbons has a boiling point temperature of 287 degrees Celsius, whereas the pentane has a boiling point temperature of only 36 degrees Celsius. So let me know if you have any questions.